1. Metric spaces. Problem 1.2. Stereographic projection. Let d sub 1 be the Euclidean metric on R, defined by d sub 1 of st equals the absolute value of t minus s. Let d sub 2 from r times r to the interval from 0 to infinity be defined by d sub 2 of st equals the absolute value of arctangent t minus arctangent s for all real numbers s and t. We want to show three things. Part 1. The function d sub 2 is a metric on R. Part 2. The metric spaces r d sub 1 and r d sub 2 are equivalent. That is, they induce the same open sets. Part 3. The metric space r d sub 2 is not complete. Solution. Part 1. We check the three metric axioms. First, d sub 2 of st equals 0 if and only if s equals t. Indeed, if s equals t, then arctan s equals arctan t, so the absolute value is 0. Conversely, if d sub 2 of st equals 0, that is, the absolute value of arctan t minus arctan s is 0, then arctan t equals arctan s. Since the arctan function is injective on R, we must have t equals s. Second, symmetry. For any s and t in R, d sub 2 of st equals the absolute value of arctan t minus arctan s. This is the same as the absolute value of minus arctan s minus arctan t, which is just the absolute value of arctan s minus arctan t. So d sub 2 of st equals d sub 2 of t, s. Third, the triangle inequality. Take three real numbers, s, t, and u. Write a equals arctan s, b equals arctan t, and c equals arctan u. Then d sub 2 of su is the absolute value of c minus a. We can write c minus a as c minus b plus b minus a. By the triangle inequality in R, we get the absolute value of c minus a is less than or equal to the absolute value of c minus b plus the absolute value of b minus a. In other words, d sub 2 of su is less than or equal to d sub 2 of st plus d sub 2 of t u. We have checked non-negativity and separation, symmetry, and the triangle inequality. Therefore, d sub 2 is a metric on R. Solution. Part 2. We show that d sub 1 and d sub 2 define the same topology. First, we show that every d sub 1 ball contains a d sub 2 ball. Fix s in R and let r be greater than 0. By the mean value theorem, for any t in R, there is some point z between s and t such that the absolute value of arctan t minus arctan s equals the absolute value of arctan prime of z times t minus s. Since the derivative of arctan at z is 1 over 1 plus z squared, we get d sub 2 of st equals 1 over 1 plus z squared times the absolute value of t minus s. The factor 1 over 1 plus z squared is less than or equal to 1, so d sub 2 of st is less than or equal to the absolute value of t minus s, which is d sub 1 of st. Thus, if t is in the open ball with respect to d sub 1 of radius r around s, then d sub 1 of st is less than r, and in particular, d sub 2 of st is less than r. So every d sub 1 ball, u superscript 1 sub r of s, is contained in the d sub 2 ball u superscript 2 sub r of S. Next, we show that every d sub 2 ball contains a d sub 1 ball. Fix S in R and R greater than 0, and define rho sub S of R as follows. Rho sub S of R is the minimum of two numbers, namely arctan of S plus R minus arctan S, and arctan S minus arctan of S minus R. Because the arctan function is strictly increasing, both of these differences are positive. Hence, rho sub S of R is strictly greater than 0. Now, suppose t in R satisfies d sub 2 of st less than rho sub S of R. That is, the absolute value of arctan t minus arctan S is smaller than rho sub S of R. Then arctan t must lie strictly between arctan of S minus R and arctan of S plus R. Using again that arctan is strictly increasing, this implies that t lies strictly between S minus R and S plus R. So the absolute value of t minus S is less than R. In other words, whenever d sub 2 of st is less than rho sub S of R, we also have d sub 1 of st less than R. Equivalently, the d sub 2 ball u superscript 2 sub rho sub S of R of S is contained in the d sub 1 ball u superscript 1 sub R of S. We have shown that for each point S and each radius R, every d sub 1 ball around S contains a d sub 2 ball around S, and every d sub 2 ball around S contains a d sub 1 ball around S. Therefore, the two metrics d sub 1 and d sub 2 induce the same open sets, and so the metric spaces R d sub 1 and R d sub 2. Solution, Part 3. We show that R d sub 2 is not complete. Consider the sequence x sub n defined by x sub n equals n for natural numbers n. If m is greater than n, then d sub 2 of nm equals the integral from n to m of 1 over 1 plus t squared dt. This integral is less than or equal to the integral from n to infinity of 1 over 1 plus t squared dt dt, which equals pi over 2 minus arctan n. As n goes to infinity, arctan n tends to pi over 2, so pi over 2 minus arctan n tends to 0. Hence, d sub 2 of nm can be made arbitrarily small by taking n and m large, and the sequence x sub n is Cauchy with respect to d sub 2. Suppose for contradiction that x sub n converges in R with respect to d sub 2, and let x be its limit. Then d sub 2 of nx tends to 0 as n goes to infinity. But d sub 2 of nx is the absolute value of arctan x minus arctan n. Taking the limit, we get that 0 equals the absolute value of arctan x minus the limit of arctan n, which is arctan x minus pi over 2. Therefore, arctan x equals pi over 2. However, there is no real number x whose arctan is exactly pi over 2. Thus, we have a Cauchy sequence in R with respect to d sub 2 that does not converge in R. Therefore, the metric space R d sub 2 is not complete.